Welcome everyone to this colloque des sciences mathématiques du Québec. My name is Léo Belzile. I'm the co-organizer of this series of event, and it's a great pleasure today to welcome Professor Aaron Smith from the University of Ottawa. So Aaron is a specialist of applied probability, Markov chain Monte Carlo methods. He's done PhD at Stanford with Percy Diaconis, and he's worked a lot in recent years in advances. And today he's talking about free lunches. Okay, but is there something as a free lunch?
Yeah, exactly.
That's the question. So thanks a lot, Darren, for accepting our invitation. The floor is yours.
So thanks very much for the invitation. Yeah, so I'm going to be talking about these things that I call free lunch theorems. Before I get rolling, I'd like to make sure I thank everybody who's helped me out on this, which is a pretty long list in this case. So the people in red, these are people who are co-authors on papers that have free lunch basically in the title. This is really what I'm talking about. But this has been a bit of a hobby horse of mine for several years. And so the people in black are other co-authors who I've asked lots of questions about and who have helped me out on some of these issues as well. All right, so I've been told this is supposed to be sort of a talk for a general mathematical audience. So I don't want to assume that everybody here knows what MCMC is, although obviously there are lots of people in the room who think about this a lot of the time. So in order to really get into the research problem, I want to say what MCMC is. I want to talk about a specific applied problem. I want to talk about the way that people usually do theory around that applied problem. And then I want to talk about why, at least for me, the theory feels a little unsatisfying or at least incomplete, and I want to do things in a different way. That feels like a lot of stuff to say before I get into any of the details. So I'm going to instead say things at a very sort of informal level first, and then dive into the notation and get to the new results really towards the end of the hour. Fortunately, that's not so hard to do. So the thing that really you need to know is that MCMC is an algorithm that's used in Bayesian statistics and many other places to do approximate integration. Okay, and Bayesians have run into this problem over the last 10, 20 years that everybody else in statistics and machine learning and so on have run into, which is you have a nice algorithm that works very well for small data sets, your data set gets big, and the algorithm doesn't work so well anymore, or perhaps it breaks completely, right? So that's a common problem. Lots of people have run into this issue, and lots of people have worked on it for many, many years. I'm going to jump on one particular thread of this problem that I think started around 2014 when a bunch of Bayesians started tackling this particular problem in one particular way. And there have been a couple hundred papers since then, more or less following along in this thread. And so I'm going to pick on Kara et al. Because they were relatively early and they have a really nice introduction if you want to read it. And they ask, can we use data subsampling techniques to make MCMC faster when faced with very large data sets? So that's the question. And obviously, they were sort of optimistic about being able to do so. And I think that that was basically the right thing to think at the time. There are a lot of stories that you can tell about why this is something that you should expect to work. I'm going to go through one of those stories on the board, but you can certainly see other ones. So to set a little bit of notation and a little bit of history, this problem of scalability is one that Bayesians haven't focused on a huge amount, but people in machine learning, it's been very, very central to work in that area. And so they started thinking very serious about the problem before it became a central area in Bayesian statistics. And they ran into the same issue, and they had a really nice answer. Simple answer. So if you're looking in machine learning, one of the central things to do instead of doing integration is to do optimization. And the basic workhorse algorithm there is gradient descent, which is pretty easy to write down. So let's imagine that I'm doing statistics. I have a function pi, which is of this form. That is, it's a product of a bunch of small objects, where each of these are the data, although you don't need to know that right now. It's just a product form. Okay? And if I want to minimize this, I can take logs, so this product becomes a sum. And if I want to optimize this, here's a natural algorithm to do. I make some guess, theta 1, and then I'm going to incrementally make my guess a little bit better by updating according to this rule. Theta s plus 1 is theta s plus something times the sum of the gradients. Okay? And if I keep on doing this under some reasonable conditions, you converge to the right answer. Okay? The problem with this algorithm is that usually eta is very small, so the steps are very, very small, and n can be very, very big, so you're adding up a lot of things, so every step is very computationally expensive. There's an obvious fix to this, which is instead of looking at the sum of everything, at every time step, you choose only a random subsample of your data, and you compute only the terms that sit in that subsample. Okay? And it turns out to be the case. So obviously that algorithm is easy to run. It turns out to be the case that under reasonable conditions, this offers a genuine speedup. That is, doing this for appropriate eta for appropriate d, you really get a fast algorithm. Moving over to Bayesian land, there's an algorithm called the Langevin dynamics, which looks really, really similar to gradient descent. It's the same formula, except I have this extra error term where I add a little bit of randomness at every time step. And so if you look at this and this and this and this, we've made a little box. And you might think I should just fill in the box. And that gives you an algorithm called the stochastic gradient Langevin dynamics, which is faster per step than Langevin dynamics and maybe does something nice as well. And it's at least okay to do, right? This is an algorithm that people use. I use this algorithm, and you would hope that it would solve this problem in the same way that SGD solves the problem with GD. Okay, cool. Reason to be optimistic. And it's not unreasonable. But pretty quickly, people found, okay, this wasn't performing as well as you might pray. Okay? And I'm going to give Michael Betancourt credit for jumping on this both very quickly and very, very hard, saying there's a real problem here. That is, integration is not the same problem as optimization, and things that work on this side of the board may not work on that side of the board. Actually, he was a lot stronger than that. They definitely don't work. There's a catastrophe, according to him. Okay? So that's sort of where I got interested in these things, and this is really the applied problem, but okay, I have a math PhD, so I want to turn this into a theory problem. And so I want to try to figure out, can I answer Carter's question and write down some mathematical framework here? And I have a problem as a math person doing this, which is when I frame the problem carefully, no, it is on this board, I want to make sure that I avoid degenerate answers. What's a degenerate answer? There are a lot of them. I'm going to go over some of them today. But just to give a silly one, right? If you take Carter's question completely literally, can we speed things up? The answer is obviously yes. Here's an algorithm. I take my huge data set, I throw almost all of it in the garbage, and I run my old algorithm on what's left. Definitely that's faster, but I don't think that's a satisfying conclusion, right? So I want to make sure that when I have theory, I don't accidentally do that. Nobody's going to do exactly that. But it's surprisingly easy to come up with algorithms that sort of secretly are doing more or less that. So I want to make sure I've avoided that issue. Furthermore, just to keep my own sanity, one thing that I said is that there are hundreds of papers talking about more or less this issue. The papers are often fairly long and fairly sophisticated. So if somebody writes a 50-page algorithm, okay, it takes me some amount of time to read the thing, then it takes me some amount of time to analyze the thing, and then it takes me some amount of time to write the paper, and in that time, there are 80 new algorithms out there. So if, as is the case, I think that these things often don't work very well, or at least they don't work as well as you might pray, I don't want to be playing whack-a-mole, right? So how do you do that mathematically? Well, the idea is to prove a theorem where instead of saying this algorithm over here has this performance, you say, okay, this statistical problem has the following property, and any statistical algorithm with that property is not going to have an algorithm in this class that works. So you can sort of wipe out a whole bunch of problems, a whole bunch of algorithms all at once if things go well. All right, so that's at a high level the game plan. I'm going to give a little bit of an introduction to the area. Like I said, I don't assume people here do MCMC, so one way to get around the overwhelming complexity of these algorithms is just not to face it. So all of the algorithms and all of the statistical problems I'm talking about today are what I'd call cartoon algorithms, right? They're not serious things that you would really use, and the methods are also mostly not serious methods, okay? The things I'm saying do generalize fairly far beyond the things that I'm going to be talking about. Certainly they generalize to work on Carter's paper and some other things that were published around the time. They don't generalize infinitely far. Towards the end, I'm going to talk about some of the non-generalizations that are most interesting to me, but 100% I've missed things. So I'm sorry, there's just no way to cover all of the overwhelming things all at once and to say these theorems in full detail. So this is what I'm going to do. All right, great. That's the high level, the plan. In terms of the rest of introduction, like I said, I don't want to assume people know what MCMC is, so I'm going to try to teach a 5-minute course on all of Bayesian computational methods. Okay, we'll see how that goes. And once we have that down pat, we can revisit the problem and make it a little bit more precise. So first of all, what's the setup when we're doing Bayesian inference? So we start off with a family of models. So for example, we might be looking at all of the Gaussians with variance 1, but unknown mean, right? A family of distributions. Then if we're Bayesians, we need to set up a prior distribution. That just means any probability distribution at all on the parameter space. So that can be Gaussian again. Why not? I like Gaussians. Then we're doing statistics. What happens? We get to see a bunch of data, x1, x2, dot, 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 which we're going to assume for now are sampled exactly from one of the models in that parametric family. So they're really Gaussian with some mean. And then the problem in statistics is, given that I get to see the data, I want to say something about the parameter that they were sampled from. I want to guess what the mean is. When you're doing Bayesian statistics, when you're actually doing the algorithm, more or less this boils down to computing an integral. Okay, not quite right, but pretty close. And the reason that computational Bayesians have a job is that unless you're doing this Gaussian example, you usually can't actually compute the integral by hand. You need to do it with a computer. And so that sometimes is hard. So that's the setup. I said that I was talking about MCMC. I need to do the first MC, then I'll do the second MC. So the first MC is Markov chain. So I just really want to set notation here. So the Markov chain is a sequence of random variables. I'm going to say theta 1, theta 2, theta 3, dot, 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 dot. And the way that you build a Markov chain is you have to specify a rule for getting theta t plus 1 from theta t. The thing that makes it a Markov chain is that theta t plus 1 is generated according to some rule only from theta t, not from all of the earlier stuff. And that's also what makes it sort of easy to do on a computer. To give the simplest Markov chain that I can imagine, I imagine a Markov chain where my state space theta is 2 points, red or blue. Okay, so here's what the Markov chain is. Hopefully, sorry, now I have to walk around so I can point at things. Oh, no, this is not going to work at all. All right, so I have a Markov chain on 2 points, red and blue. So let's imagine I start theta 1 as red. What's going to happen with probability 0.3, my next point is blue, and with remaining probability 0.7, my next point is red. And then I just keep on doing this, right? Whatever time t I'm at, whatever point theta t I'm at, I look at that ball, and then I follow the arrows. And that's it. It's really annoying to draw this picture, so of course we need some notation. I denote by K the transition kernel or transition matrix for that Markov chain. What does that mean? Every row of that matrix just gives you all of the probabilities of jumping to the next state. Okay, so the first row is the row corresponding to I am currently in the red ball. I don't even want to write the matrix down all the time. So when I'm talking about this for the rest of the talk, I'm just going to say I have a kernel K, and I'm going to use this notation theta 2 plus 1 tilde K of theta T dot to say I'm sampling from the distribution corresponding to the theta T row of the matrix K. Okay, that's all the notation. Now you'll notice I lied when I was setting up this notation. In the previous slide, theta was the reals. Here it's finite. So I don't have a matrix, right? I have this other object. If you know what a kernel is, it's a kernel. If you don't know what a kernel is, you can think of it as a matrix. It's not going to really change anything for the rest of the talk. Okay, so that's the first MC, Markov chain. Second C, Monte Carlo. What do I do with these things? I'm going to assume that somebody, an angel or whatever, has handed me a transition kernel K with the following property. If I keep on sampling theta 1, theta 2, theta 3, dot, dot, dot for a long time, the distribution of my tth random variable is going to get close to the measure pi that I'm interested in, this posterior distribution. Let's assume somebody has handed me that. What do I get out of that? Well, I'm interested in computing integrals. So the obvious estimate for an integral given a bunch of points is just to take the sample average. Okay, so that's what I'm calling pi hat of f over there. If you do that, then we have, under very mild conditions, a strong law of large numbers. Pi hat converges to pi. We have under slightly stronger conditions, we have the CLT. That is, we know something about the error rate. And then two things that I want to focus on a little bit, which is what do these things look like qualitatively? So we have the CLT with this mysterious looking variance term. We know more or less what the variance is for this estimator. The top thing, variance pi of f, that's just what you would get if you were using independent samples. I'm going to ignore that for now. The thing on the bottom, 1 over 1 minus lambda over k, that's the penalty for using Markov chains, right? We don't want to use Markov chains. We're forced to use them because we don't know how to do this otherwise, essentially. What does the penalty look like? If k is a matrix, there's a general theorem which tells us, under some conditions, the eigenvalues of the matrix are strictly between -1 and 1. Exactly one of those eigenvalues is 1. Lambda here is the biggest eigenvalue that's not 1. Usually it's very close, like 0.997 or something along those lines. So 1 minus lambda is tiny. So 1 over 1 minus lambda is big again. So this is a large penalty that you get for using a Markov chain. The key thing that I'm going to be using here technically is that asymptotic efficiency depends on this lambda k. And that's the same lambda, more or less, that shows up in the exponential convergence. That is, not just theta t converges to pi, but theta t converges to pi at some exponential rate. And it's the same lambda that shows up in both of them. Last thing I needed to talk about, which is where does this kernel k come from? So I've written down sort of the first general algorithm that people wrote down for doing this. It's called the Metropolis-Hastings algorithm. There are two things that I need you to see from this slide. The first is, as a general picture, where are we getting these things from? The answer is you start off with a very simple Markov chain, which I'm denoting by Q. So Q of theta dot might just be sample a point that's uniformly that's close to theta, something that's very simple, obviously does not have the right stationary measure. And then this gives you a recipe for tweaking the output of that algorithm to get something with the right stationary measure. Okay, so that's the first thing. The second thing is, what's the hard part here? In step 2, you notice that I have to compute pi of theta star over pi of theta t. So I have to evaluate the likelihood twice, more or less. That's going to be the hard part because that involves taking a product of n terms. Okay, so this is a toy algorithm. People don't use exactly this very much these days, but that story turns out to be true more or less for a lot of real algorithms. Okay, so even though this one's toy, the real ones have the same basic structure. All right. All of that was Stats 101 for people who haven't seen that before. I'm now going to switch and talk to the other half of the room and talk about what the running examples are. If you haven't seen the previous stuff, this is probably not going to make sense, but I do want to at least say what the prototypical examples are so people have concrete examples in the back of their head. So the first one is, what sort of models am I going to be dealing with? Here are two you can have in your head. First of all, the usual Gaussian mean problem. And second of all, doing logistic regression, say in one dimension, but actually any fixed dimension is fine. Okay, these are sort of prototypical simple problems that all of the results I'm talking about are going to apply to. In terms of algorithms, you can think of the Metropolis-Hastings algorithm with proposal variance scaled to the size of the data set, and similarly the unadjusted Langevin algorithm with proposals scaled appropriately. Great, now we know Bayesian statistics. We can go back to Kordakar's question. Right? Korodakar was asking, can we make MCMC faster? If we want to turn that into math, we have to say what fast is. Fortunately, it's not so bad here. We're running a Markov chain. We get some answers that are converging, right? These pi hat of f's that are converging to the right answer. So we can talk about how many steps it takes for pi hat of f to be very close to the right answer. Okay, so that's how many steps you need to run. I'll call that tau. And then we're computing, when we're running the Markov chain, right, we're computing this theta t plus 1 given theta t many, many times. So we're going to do it by c, the cost of doing that once. There's a little asterisk here. For most of these algorithms, including Kordakar's, that quantity is random. I'll deal with that a little bit more carefully when I start writing down actual theorems. It doesn't vary very much, so we can think about it as constant for now to get the flavor. For all of the prototypical algorithms and examples that I wrote down on the previous slide, it's not very hard to prove that tau scales like epsilon to the -2 independently of n. There's no theory for what c should be because it's not very carefully defined, but the hard step is clearly computing this product here. And so it makes sense to say that the cost is basically linear in n. Okay? For a large n, this is very close to right. Okay? So that means when we're talking about faster, what we mean by faster is faster than n times epsilon to the -2, right? That's the thing to beat. So we can rewrite the question. We want to say we're faster than those prototypical algorithms. And the proposed solution is to break the bottleneck by doing subsampling. Actually, I basically said what that was a while ago. What do I mean by subsampling? When you're running Metropolis-Hastings, every single step that you take, you're computing this thing twice, right? So all that I do is at every single step, I choose a subsample of my original data set. I'll call it D, and I only use those things just plugging into this formula. Okay, I only use those things when I'm plugging in. All right. There are a couple of ways that you could do that. I'm going to distinguish between two of them. The first one is noisy MCMC. This does exist really in the literature, where at every step of the Markov chain, I choose an independent sample. and I use that same independent sample every time I need to look at the data in that step. Another thing you could do is what I'm calling naive MCMC. This doesn't get used anywhere in the literature, which is I just throw out a bunch of the data before I do anything, and I run with that subsample forever. Okay. People do more sophisticated things, but this is close enough. I said I wasn't going to get into real algorithms. Okay, I lied a little bit. I want to say at least a little bit about one tweak to this procedure, which is doing pre-computation. So in practice, when you run MCMC, usually it's computationally annoying to take a standard algorithm and apply it directly to whatever your model is for a bunch of different reasons. And so people usually do pre-computations to make the calculations nicer. In the context of subsampling, there's a sort of an obvious thing to do, which is to take all of your data and compute some control variates. And a popular type of control variate is a global surrogate. So that is, you train one model that is close to the full posterior. And then when you're running subsampling MCMC, every time that you would use a plugin estimate, you shrink that estimate towards the global surrogate. Okay? So this is sort of a variance reduction type technique. So finally, we can get back to the motivating question and say the version where I'm going to try to say an answer, right? Can we use subsampling MCMC to get faster algorithms for large data sets? And if we're doing this, we sort of want to make sure that we're doing at least two things, right? The first one is it has to be accurate, right? We can't say that we're just throwing away a bunch of the data, right? That doesn't count. So if that doesn't count, then any other algorithm that is less accurate also doesn't count. Okay? The second thing we have to do is that we actually have to use the MCMC part. So I said in the last slide that sometimes we compute a global surrogate, right? So here's another dopey way to get around the question, right? You compute a global surrogate, and then you just sample from that thing. That can be very, very fast, but you're not using the MCMC part. So you have to do both of those things. You have to be more accurate than just throwing away data, and also more accurate than just using your global surrogate, and more accurate than doing both of those together. And then we want to know if after all of that, you can still be fast. And our first answer is basically no, this isn't possible. Okay, that is, for a broad class of problems, there is no nice algorithm which can sort of both be fast and be more accurate than those two reasonable alternative strategies. Okay? In order to do that, I had to add a lot of words in red, right? These sort of caveats. And if you take out these caveats, then the conclusion starts becoming false. Okay? So you do really need at least many of these things. Okay? I'm not going to go through all of them carefully right now, but I'll say most of these caveats are caveats that I think really should be there if we're going to develop a good theory. And a few of them, unfortunately, are just technical places where I can't do the math personally. I run into difficulties. So the first two words, I think, are sort of a good example of two extremes in that direction. The first one is the word reliably. Okay? So we can't reliably make things faster. Why does that need to be there? Well, it goes back to thinking about degenerate answers again, right? I'm trying to compute an integral, right, associated with some data. So here's an algorithm for computing an integral, 4. Whatever you give me, I'm always going to tell you the integral is 4. That's a very fast algorithm. I don't even need a computer to do it, right? And sometimes it's really good. If the integral is 4, that's a great algorithm. But if you change the data, it's not going to be the right answer anymore, okay? So there are all these degenerate situations where you can have algorithms that are very, very good for one data set, essentially by chance. I don't want to include that, right? That doesn't count as answering the question. The next one is exactly the opposite. So this one is reversible. This is a technical word that's just about sort of some property of the algorithm itself that I'm not going to say carefully. I really want to get rid of that word. It doesn't belong in the theorem. I don't know how to do it. I'm running into technical problems there. Okay? Most of these words are closer to reliable than reversible. That is, there's things that I think really need to be there to have a theory that isn't degenerate. But that one I want to get rid of. We have had some success doing that. So actually, for the unadjusted Langevin algorithm that I wrote down 5-ish slides ago, we can actually analyze these prototypical problems, and you can get rid of the word reversible. Okay, so that is, our theorem does hold often for non-reversible things, but you do need some fairly strong assumptions. We're sort of in this mode that I call playing whack-a-mole, where we can do it for specific algorithms and specific problems, but we don't know how to do it in any sort of sufficiently large generality. For the small number of people in the room who are interested really in this particular type of problem, this might be sort of familiar. There's another paper by Nagapetyan et al., which gave essentially the same answer when studying specifically stochastic gradient Langevin dynamics. Okay, so the first thing I want to say was to acknowledge that. They definitely talk about the same phenomenon as what we're talking about. But I also want to draw a distinction between what they do and what we do. The first distinction is that they're playing whack-a-mole. So that is, they're specifically going after SGLD. And moreover, they're going over a fairly simple version that's not terribly popular, where you don't have control variates or do any other sort of fancy techniques. If you were to try to do that with their algorithm, with their analysis, it gets difficult very, very quickly. It's not so obvious how to extend things. Another thing, this is maybe a little bit more technical, is that if you read what they actually do in the paper, they don't prove that SGLD is actually inaccurate, right? That's what you want, right? If you're trying to prove an algorithm doesn't work, you want to prove that the answers are actually bad. They don't do that. Instead, they look at an upper bound on the error, and they prove the upper bound is large. Okay, there's an obvious problem, right? Which is the upper bound in the error could be large because the error is large, or it could be large because it's a bad upper bound, right? So it's hard to tell what's happening. So we actually talk about the error itself and show the error itself is large. Now, there's a trade-off. Our results are way more general, and we go after the actual error. Our constants are worse. Our paper is much harder to read. Okay, sorry. But that's what we're doing. All right, so talk so far. So like I said, there's a sort of typical MCMC, which has running time n times epsilon to -2. There are various sort of standard tricks for getting around them. And we've said that those standard tricks, really, you can't do much better. Okay. Rest of talk, let's go into some of the details, see what the theorems really look like. So first of all, I want to say what people did first. This is what I was talking when I was saying 4 things at the beginning. I was saying I would talk about the standard way of analyzing these problems. So first of all, I want to say what is the standard way of analyzing them, and then say why I find it a little unsatisfying. So here there's a result that many authors have proved versions of. Okay, I'm not going to try to say all of them precisely, but they say something like this for the standard algorithms. If you're running noisy MCMC, for these standard problems, then you can get an error of size epsilon with computational cost of about epsilon to the -4. Okay? In particular, you have this running time that doesn't depend on n at all, right? Whatever error epsilon you want, you can do it independently of n. And in some sense, you can declare a victory at this point, right? You've solved the scaling problem. You've got error estimates that don't depend on n. And that's true, right? There's nothing wrong with these results. But I find them unsatisfying. Why do I find them unsatisfying? Well, before I wanted to talk about 2 types of subsampling, right? Noisy subsampling, which people use, and naive subsampling, where I just throw a bunch of the data out at the beginning. If you plug naive subsampling in through these theorems, you get exactly the same answer. And when I say exactly, I don't mean, within a factor of 2. I mean exactly the same answer. And there's a reason for that. The common way to prove these sorts of results is via something called perturbations. And the idea there is you take a kernel K and your noisy version of the kernel, K noisy, and you try to see what the error of the approximation is. And then you just add that error up for some number of steps until you get cancellation. And if you're doing naive MCMC or noisy MCMC, the 1-step error is exactly the same, right? Those algorithms only differ in the fact that you're resampling the error. But if you're doing 1 step, you don't see that at all. So you get the same answer. I've already said that I think it's very unsatisfying to do naive MCMC, right? I don't think that's what anybody is looking for. So any theory which gives you the same guarantees is a theory that I find unsatisfying. It's not that it's wrong, right? But it's not getting us sort of the qualitative answers that we probably want. It's natural to ask, can you do anything easy to save this? The answer is a little bit complicated, right? One thing you might do is see, can I get different answers if I use control variates? Remy Bardonnet wrote a nice paper analyzing some simple approaches there, and the answer turns out to be basically no. You might try to use very complicated control variates. There's a lot of work in that area as well. And the answer for that turns out to be, yes, if your control variates are sufficiently complicated, it is possible to really do much better. But actually, at that point, you don't need the MCMC part at all. You can just use the control variates. Okay? There are a lot of things in between those two. As far as I know, which is certainly not everything, nothing easily gets around these sorts of results. Okay, so that's sort of a prototypical result of what I call sort of a standard analysis. What are we doing? We're doing something that's a little bit messier. So I need a little bit of notation here. So what I'm going to do is the following. I'm going to fix this family of algorithms K sub x. So that is for every data set x that I have, I'm going to have some algorithm K sub x, and I'm fixing that algorithm ahead of time. Okay? I need to do this for the reliability issue I talked about before, because I need to talk about all possible data sets. I can't go data set by data set if I want to get a non-trivial answer out at the end. Given that, I'm going to note by sigma x the number of steps I need to take from k sub x to get a small error, say less than 0.25. Next, I'm going to let tau sub x be the expected number of steps to use at least m data points, where m is something that's not too close to n. All right, what does this mean, use? Okay, in the paper, the definition of use is 2 pages. I'm not going to subject you to that. Informally, what's going on here? When we're talking about these sorts of simple algorithms like SGLD, right? At every time step, we're choosing a little subsample, okay? So a data set gets used, a data point gets used if it's in that subsample. So tau sub x is the amount of time it takes for the union of those subsamples to be large, to be of size roughly m, okay? Why don't I just say that tau is m over the size of d? The answer is because it turns out for most of these algorithms, including the one that Koratakara actually wrote down, you don't fix a uniform d all the time. Instead, the number of data points that you use per step changes quite a lot. Okay, so at this stage, I'm going to be a little bit more careful in my analysis and allow for variable sizes. Okay. Otherwise, the definition is, I hope, the one that's sort of natural. And finally, I'm going to let T be this sort of pre-computed Laplace approximation, this global surrogate using a Gaussian. And my heuristic is that the running time of this sort of algorithm is sigma, the number of steps I need to take, times n over tau. That is the average number of data points that I used per step so far, times something depending on the error. And just for reference, for these default algorithms for the D-sharp problems, tau is exactly 1. I use all of the data, so it takes 1 step to use it all. And sigma is also close to 1. That's a theorem that's not obvious, but true. What do we do? Here's a theorem, which I'm going to unwrap. Okay, so I'm going to start off by saying I'm talking about reversible algorithms. That's a technical word. I'm going to say I'm talking about exact algorithms. What does that mean? It means that when I'm running the Markov chain, I'm going to be converging to some distribution. I say the algorithm exact is if the distribution that it converges to is equal to the distribution that I want it to converge to. There's no asymptotic bias. Okay? The prototypical algorithms I wrote down before, things like stochastic gradient lineage and dynamics, if you don't correct them, those do have bias. Okay? So this doesn't apply to like noisy MCMC. It does apply to some algorithms that people have written down. Okay, we're going to get to noisy MCMC on the next slide. So I'm going to talk about reversible exact algorithms. Let's look at what's on there. Inside of the probability, ignoring the probability part for the second, I say n sigma over tau is bigger than n over log n. N sigma over tau was what I called the running time of the algorithm. So that thing in the middle says n sigma over tau, the running time is bigger than n over log n. And for reference, the running time for sort of a default algorithm is n. So when I say you can't get much of a speed up, that's what I mean, right? The running time is at least n over log n, roughly, and we already have an easy algorithm that has running time n. So at most, you're getting a log n speed up. I'm going to keep on ignoring for the probabilities and go to the next line. What that says is that for specific existing algorithms, we can get rid of the log n. So the first result is sort of a generic result, no matter what paper you write in the future. We have this bound. But we also looked at specific papers that have actually been written and tried to figure out, is the log n real? And the answer for all of the ones that we've looked at, both the ones we analyzed in the paper and the ones that we did just on our own time, the answer was no, the log n wasn't real. You can get rid of it, and actually pretty easily. I suspect that's true in some great generality, but I wouldn't know how to prove it. Okay. You look unhappy with that. No, okay. So that's sort of the result, okay? So you can never get a big speed up, and for specific algorithms, we can check you really can't get anything. Okay, there's a probability outside in the end. Why is that there? Like I said, for specific data sets, there can be specific algorithms where you get lucky and you get something that's very, very fast. This is quantifying how lucky you have to be, and the answer is very lucky, right? N to the minus 2 is summable, that's why I chose it. So what this says is asymptotically, almost surely, you don't get a speed up. You might get it for a few small values of n. Okay, that theorem only applied to these exact algorithms. Most of the algorithms in this literature are not exact, okay? So we need to change the theorem. The place that I'm going to change the theorem is in the assumptions. So everything in the result is the same, except I've replaced the single word exact for the stationary measure is exactly the posterior with this long condition in red. Okay, I'm going to ask you to ignore it for a second and let's just see what this is really talking about, right? If you have a non-exact algorithm, you're going to have some amount of bias, right? And what you can do is compare the following, right? I have two ideas that I could do. I could take the actual data that I have had, the first M data points, the one that I've seen up until this point. And what I could do is I could say, great, now I'm going to resample the rest of the data. So I have my actual data set D, and then I can resample. I can get this fake data set D tilde, which is sampled from the same distribution as D, conditional on the first M data points. Okay, so I have my original data D, my new data set D tilde. And from the point of view of the Markov chain, these are identical, right? The Markov chain has only seen these M data points. Okay, those data points D and D tilde have their own posterior, pi and pi tilde. Okay, and then I have in the middle the stationary distribution of the Markov chain. From the point of view of the Markov chain, right, both D and D tilde are equally plausible. So there's no way that the stationary distribution of the Markov chain can be closer to D, at least much closer to D, than it is to D tilde, right? Because it can't tell the difference between them. So what does that tell me, right? If that's right, the difference between this posterior distribution and the stationary distribution has to be at least as big, roughly, as the difference between that posterior and the fake posterior. What this red condition is saying is this theorem is true as long as the stationary distribution for the Markov chain is closer to the posterior for the original data set than it is for the posterior given this fake data set. What does that mean informally in English? It means the stationary distribution of the Markov chain saw more than M data points. Okay? So I said way back at the beginning, I want to be able to say, right, it doesn't count if you just threw away the M data points. But I needed to turn that into mathematics. This is how I turned it into mathematics. The stationary distribution of the Markov chain has to be better than the distribution that you would get based on throwing away all but M data points. Okay, that's the condition there. And then the rest of the theorem is literally identical. What's the point? So what these theorems are doing is they say we have these sort of general conditions on the model, right? These standard models, and on the test statistics, like this Gaussian global surrogate. And as long as you satisfy these conditions, we could say that no algorithm really beat this standard. Now, I don't mean it can't beat any dimension. But I mean, if it beats the standard one, then actually you can replace it by one of these other standards, right? So if you want to make it faster, you can throw away data, right? If you want to use a global surrogate, you can just use a global surrogate. But you can't do better than all of those simple things simultaneously. And the nice thing is I don't have to play whack-a-mole anymore, right? That is, I just have to look at the model. I don't have to look at the algorithms. I like looking at the algorithms, but you don't have to. All right. If I was talking about this sort of stuff just to statisticians, I usually stop around here. But this is supposed to be, I think, a math seminar, so I should talk about, one non-trivial theorem and where some of these results come from, at least for, 2 minutes. So I'm going to say two things. The first is, if you ignore all sorts of stuff about interchanging limits and integrals and so on, all of the analysis work, why should we expect this to be true? Because it turns out there's a pretty easy calculation. And then I'm going to talk a very small amount about the main technical tools that we actually used to do the hard stuff. Okay. So the first part is the sort of counterfactual idea that I was just saying before, right? After t steps of the algorithm, you've seen the pre-computed work, and you've seen a bunch of the points of the data set, but not all of them, right? But not all of them. And so I can make this sort of counterfactual data d tilde. And as I said before, you can't distinguish between d and d tilde based on only looking at the Markov chain, right? That's what d tilde is. And so that means that the distribution of the Markov chain can't be closer to the posterior than these two posterior distributions are to each other. Okay, I get that inequality that's right in the middle of the slide. Approximate. I lose a factor of 2 or so there. Okay. One thing that I need in this slide that I didn't have in the previous slide is that that's true for a particular time t, right? The amount of time it takes to see m data points, roughly. Okay. So what this means is for a particular sort of intermediate amount of time t, when I've seen most of the data, but not all of the data, I get a lower bound on the distance to the posterior distribution. Okay, but we know that Markov chains converge exponentially quickly to the posterior distribution, which means that if you know that it's far from the posterior, or at least not extremely close to the posterior after some number of steps, then you can bound the rate of conversions. This is just an exercise, right? This is algebra. And we get something like that. 1 minus lambda k is less than log n over n. Okay, but recall way back from Bayesian Stats 101 that the asymptotic variance of an MCMC method is proportional to 1 over 1 minus lambda k. So knowing this for a particular time t that I've chosen very carefully actually tells you what the asymptotic variance looks like, tells you what the error is for all large t. So there's this nice laundering that happens where you go from medium values of t to very large values of t. Okay, that's heuristic, but more or less one can make that true. What's the hard part of the paper, the place where I spent a lot of time in the middle of the night being unhappy? The main problem is sort of the following, right? I need to check, right, that these posteriors are actually far apart from each other. And when everything is Gaussian, I can just do the calculation and life is easy. But for these real applications, it isn't that easy. So first of all, when I'm conditioning on this complicated thing for a complicated model, it's not clear how to write down the conditioning in any explicit way. Okay, I can write down a definition, but nothing that I can calculate with. What I need to do is I need to check that the fake data d tilde is actually not close to the original data. So how do I actually do that, right? How do I get a lower bound on these differences? The next thing is, let's assume that my data and my fake data are far apart from each other. Can I check that the posterior distributions are far apart from each other? Now that one seems goofy for a second, right? If my data isn't close to each other, surely the posterior isn't going to be close to each other typically. Okay, except I'm looking at real algorithms here, right? So people did all of these pre-computations, which are exactly designed to say, I don't have to look at the data to make the posteriors close to each other, right? Looking at the surrogates is basically good enough. Okay, so it's true, a generic perturbation of most models is going to change the posterior, but I'm specifically looking at things that are not generic perturbations. They're about as far from generic as it's possible to be, right? They're designed to make step 3 not happen. Okay, so what do we do to actually measure that sort of thing? And then finally, if you go back to the previous slides, if you were trying to make them careful, it turns out that actually just having one d tilde isn't good enough. You actually have to have a whole family of these d tildes that all work simultaneously, or at least most of them work simultaneously. That's not so obvious, but it's true that you need something along those lines. Okay. How do I deal with this? There are really sort of two ideas. The first one is I use random matrix theory to approximately linearize the problem. So that is, there's all this work on computing random matrices and their eigenvalues. If I can get reasonable estimates on the eigenvalues associated with these conditional distributions, then I'd be happier. And then I use these tools called anti-concentration to deal with the linear case to actually get through 1 to 4. Okay. The random matrix theory stuff is unpleasant to write down. But fortunately, there's no nice theory as far as I know for doing random matrix theory for these problems. Everything is sort of by hand estimates. Fortunately for the anti-concentration, while that was true a long time ago, Shirav Chatterjee in 2018 wrote a beautiful paper that sort of made anti-concentration accessible to the masses. So I want to advertise that because it's really nice, and also talk a little bit about what we did in this area. So the idea for anti-concentration, right, this is sort of the main technical thing that we want to do, is to say, if I have a random variable u, I want to make sure it doesn't get stuck at one point, right? It's not concentrating on a very small interval. So that's the opposite of what we usually do. Right? Usually we have Hofstad's inequality. We say things are close, and that's how we show that algorithms are good. I want to show an algorithm's bad, so I want to do the opposite thing. And that's harder, right? Usually. And so how do I do that? Well, there's this sort of anti-concentration general bound from Chatterjee, which says the following: the probability that u gets stuck in some small interval AB can be bounded by two things, right? What you do is you come up with another random variable v, which has to have two properties, right? First of all, the distribution of v has to be very close to the distribution of mu. That's the thing on the far right-hand side. And second of all, point-wise, u and v have to be far away from each other. You have to couple them so that that happens. If you can do that, then you can check that u doesn't get stuck. Okay. How do you actually do that? There's a really nice construction for binomials, which shows that you can actually do this in essentially an optimal way. That is, you don't lose anything by using these sorts of bounds. Here's the basic idea, right? Here's a theorem. If I have a binomial NP random variable and a binomial NP prime random variable, I can couple those two things such that the difference between them is bigger than roughly n times p minus p prime. And the straightforward calculation tells you that the distance between those binomials is small as long as p minus p prime is less than roughly 1 over root n. So there's this regime, right, where p is sort of much bigger than 1 over n and much smaller than 1 over root n, where the distances between the distributions are negligible, but you can still couple random variables so that they're far apart from each other. Okay, and that's really what we need in order to do these constructions of our bad data sets. Okay, so that's it. Really simple results. Actually, the proofs aren't very long, and they give you anti-concentration. And here's the important part: that's basically optimal. Yes.
Can you repeat what properties you want the V to have with respect to U?
Yeah, so it's
Okay.
this stuff that's on the right hand of the top side. You need two things. First of all, the distribution of they're not very close to each other. So the distributions are close, but the actual random variables are not close. Yes. So like I said, we couldn't just deal with that the probability of getting stuck isn't close to 1. Because you have a 1/2 times 1 there, you can't do better than that, right? So you can't do something, you can't check that the probability of getting stuck is like 0.1, or the result simply doesn't say that. And so we put in a little bit of work to extend this so that you can get any arbitrary small probability that you. So that's it. That's all the technical stuff. And we talked about the only part that that really matters, which is fixing grades, right? So like I said, I have this theorem which has a bunch of conditions. You can certainly get around the conditions and the conclusions in a number of different ways, and I really hope people do that. I'm going to focus on 2 ways that you can get around it. One of them is this reversibility condition that I talked about a few times. So in the point of the proof that I was talking about before, we needed this reversibility condition to relate to the sort of rate of convergence and what happens after sort of a relatively small number of steps to the absolute variance where after very steps. So basically the change for which you have to back the extremely straight to non-reversible variables, the next connection and the arbitrary curves. But it is a really small conversion and not any conclusion. That in the paper is actually useful. As it is, all right, and we can't work with the non-reversible algorithms or like previous papers, that doesn't mean they're not fine. It just means I don't know how to prove this. This is to be the big question. Can you say anything about these algorithms? I'm going to be honest. When I started working on this a few hours ago, I was thinking 18 months from last year, oh yeah, this is going to be exactly the same. I just don't know how to prove it. And I spent some time doing future cases, and that being holding up. Until I read this paper, Johndrow in 2016, where actually, if you read it carefully, they really do manage to get around our results for this like one very specific model. Okay. So what do I know at the moment about non-reversibility? I know that for the standard algorithms or the standard problems that I wrote down near the top start of the talk, the same conclusion applies. You can't do much better by subsampling. And then for literally this one paper, okay, and I think one other, you can get around these problems. You really do get something that's faster. And in between those are literally every non-reversible algorithm that anybody actually uses, for which I don't know the answer. So as far as I know, that's largely open still at the moment. Yeah. Oh, sorry, I've lost this. Oh, all right, thank you. All right, just for the last couple minutes. The other thing I think is that it's interesting just to work on different problems. So all of these conclusions that I was talking about today were saying that the running time can't be much faster than linear in the amount of data that you have. And if you're working for these sorts of simple problems, we already have algorithms that are linear. So you can say that working with the subsampling isn't helping very much. But for a huge number of statistical problems, we don't have any linear time algorithms, right? And the conclusions of the theorem, if you push through the math, which we don't do in the paper, you would get the same conclusion, that they can't be better than linear. Okay, if your algorithm is n cubed, having me say you can't do better than linear isn't much of a deterrent, right? So those are places where it's definitely possible to get huge speedups, or at least these sorts of results can't say anything about them. So this is something that I think is extremely promising. I've been working on some stuff in this area with PhD students, and yeah, we've more or less managed to do it in a couple of cases, really with very different ways. In some places, finding better approximations for the model, and in other places, finding improved perturbation bounds for very specific families of target distributions. I don't think this is anything like complete. I feel like there's a huge amount of growth there. Last thing you can do, of course, is build, right? So at the beginning of the talk, I was talking about speeding up MCMC by subsampling. But you don't have to use MCMC. There are all sorts of other very nice techniques that people have been working on. There are various articles that talk about how what you're really interested in is problems like logistic regression with very large amounts of data, that doing MCMC is just not the right thing to do. You should use other techniques. So there's some beautiful papers about constructing surrogates in a very generic and powerful way that, as far as I can tell, work very well for these sorts of problems. So that's sort of a big thing that one. All right, that's it. So what's the closing message? So the applied point of view, I can say that there are these nice product models and these nice surrogates, and when you're in that situation, subsampling doesn't seem to help very much. As a mathematician, there's a sort of side point of view, which is to say, it's surprisingly hard to write that informal statement down very carefully. That is, certainly people have written papers proving theorems that were positive results about subsampling algorithms that somehow seem to skirt things in ways that are a little bit subtle. And then outside of this question, basically everything is open, dealing with non-reversible chains, dealing with complicated algorithms, so and so on. There's a lot that is left to do. Okay, that's it. Thanks very much.
Thanks, Aaron. Any questions from the floor?
I can ask a question.
Oh, yeah. So you mentioned something about non-reversible algorithms.
Yeah.
I was wondering what we can say about the zigzag, because when it was introduced, it was kind of the selling point, no?
100%. Yeah, and there was a nice paper on zigzag like 3 days ago.
Yeah,
On this. Yeah, I've written about this a few times. Informally, my conclusion is it's unclear. So maybe I can say this for you, and then we can talk about this in a little bit more detail later. So I'm not going to say what this is too much to say. It's a non-reversible algorithm which heavily uses subsampling, and we also use in covariates. And I think the recent paper, they have to do a little approximation of something that's verticals. And they have a bunch of theorems which are, and please correct me if I'm wrong, and I'm sorry, I have not studied this carefully, which say something along the line of, first of all, when you're running the algorithm, the amount of time back to the data is very small, so that if it's genuinely faster than doing these sort of default algorithms. And second of all, if you look at the run of the algorithm and you let the amount of data go to infinity, then that path converges weakly to the path that you would have gotten for a valid. Does that sound about right?
I think so.
All right, I'm going to pretend that that's true. Right, so these are the types of results that they get, right? So the first part is it's genuinely faster, and the second part is that it converges weakly to the right answer, and it then goes to infinity. I have no reason to doubt either of those things. I think the first of those, that is it's genuinely faster, is exactly what we want to prove, and I don't think that there's any subtlety around there. I think that the weak convergence, there's a huge amount of subtlety about exactly what's going on. The reason for that is as follows. If you were running bog standard metropolis things and you did a Laplace approximation, and you just ran it based on the Laplace approximation, the sample paths for that would also converge weakly to something that is valid. Okay? So in other words, just having weak convergence of the sample paths is not good enough to tell you that you're using all of the data. Right? In particular, it shouldn't be very surprising, because if you look at half of the data, you would also get weak convergence to the right answer, right? Somehow it doesn't matter very much. Now, this isn't to say that there's a problem with zigzag. Like I said, to me, this is the big open question as to what exactly is going on there. But those types of weak convergence results are not sort of strict enough to be able to tell exactly how much of the data is being used.
So at the moment, there is no way to connect something like that with your work.
Right, they're targeting different types of things. One thing I've done when talking to him before was looking at some previous results and saying that that problem that I just mentioned about weak convergence can actually happen. Now, Whether that happens for any real example, I really don't know.
Thanks, Aaron. Yeah, I guess my question was more on the ergodicity part. So does your result cover the case where the chain does not have an invariant measure, or?
Basically, no. I mean, one could probably do something, but I haven't tried.
Because I remember like early days of these theories, like there's some even like algorithms that were shown to be transient when you don't do the right like accept reject things.
Oh, for sure.
Yeah. So you assume you have like stationary.
This was not a mathematical thing that I really considered. Either reason, if you don't have a stationary measure, usually that diagnostic is something going on.
But that's the Mitrofanov results are all like this, like all the noisy MCMC, like I think along the lines of Mitrofanov's results, you know, like where you do the one-step comparison.
Yeah.
I think they just tell you like you will be at some point close in an epsilon of the true posterior, but you don't know if it's gonna be if it's gonna. Yeah. Okay.
I mean, not always. Okay, one has to be a little bit.
Yeah. Okay. Good. Yeah.
So you asked about talking about things which genuinely we know don't have one. And it's not that there's really always a problem, but okay, these are hard. Maybe one thing I can say about that. So if I was talking about the general paper where we keep all of these sorts of results, that's coming from work on. God, I'm going to forget the name. I'm sorry. Pseudo. Somebody can help me out.
Because you pose him.
Thank you. Yeah, it's coming from the Monte Carlo. And so those ones are maybe not going to be ergodic in like a very strong sense, and those ones do seem to actually need this. So like I said, the 10 is the only paper that I've seen and analyzed where this actually happens. Regular Monte Carlo scheme that needs this for 20 examples. But of course, Monte Carlo was published,